So that actually closed out the rotational unit. We have another kind of separate topic that we need to address in mechanics. That's simple harmonic motion. You may remember that we already did this lab, so that was kind of an introductory exploration of the idea. Hopefully in today's lecture some of the things there will become clear, and some of them they won't become clear, in the sense that I'm just going to have to tell you a couple equations that are a little bit beyond the scope of the course to derive. Harmonic motion, what does that mean? It's an oscillating motion. It repeats over and over. Now what makes it simple versus not simple? Well, that will become clear a little bit later today. That actually has a technical definition of what makes an oscillation simple versus not simple. We will be taking a look at two systems. One is the mass on a spring, and one is the pendulum. You may recognize these are the same two systems that we explored in the lab. The mass on a spring system is a true simple harmonic motion system. The pendulum sort of is, but not quite. And I'll talk about that one. That's why I talk about that in a second. We'll talk about a mass on a spring system which has no caveats or catches, and get accustomed to what's going on. And then we'll move on to the pendulum, which has a few caveats or asterisks about how it works. For both of these systems, we're going to look at three different aspects. We're going to take a look at the kinematics, which, remember what that means, description of motion. So we're going to take a look at the displacement, velocity, and acceleration, things like that, and get an understanding of how those things interrelate. Now it's going to turn out that kinematics are actually quite complicated because the acceleration in these systems is not constant. There's a reason we saved this for last, because it's by far the most complicated type of motion that we would look at. Now because the acceleration is not constant, your favorite kinematics equations, which I call the constant acceleration equations, are not going to apply, right? So that nice, huge toolkit of those 5 equations goes right out the door. You can't use them. That's why I call them the constant accelerations. It reminds you when they're good and when they're not good. In this case, they're no good. And so here, we're going to focus only on the concepts. So just the general ideas. We're not going to have any equations because we can't use the ones we had before. Luckily, we have an approach which doesn't care if the acceleration is constant. That's what allowed us to look at lots of much more complicated motion, like roller coaster loop-de-loops and things like that, and not give a care in the world. What was that method?
Energy.
Energy, right? So we're going to take a look at energy exchange in these systems. That's going to be our way of doing calculations, is by looking at energy. In these systems, there is some kind of kinetic energy being traded with some kind of potential energy. So these things go faster and slower. You've probably seen the mass on a spring at this point. If you went to that lab, you saw the mass bounces, it goes faster and slower, right? Well, it's because it's being traded, the kinetic energy is being traded with some kind of potential energy. There was one drawback, though, to the energy method. For all that it gave us, there's one thing we can't find with it. What is that?
Time.
Time. So we seem to be having a little bit of an issue. We can't get the time from here because our equations are no good, and we can't get the time from here because this can't do time. So just randomly, out of nowhere, pulled out of a hat, I will give you equations of the period, how long it takes for these systems to oscillate. And these, I'm just going to have to pull out of thin air because we don't have the tools in this class to find them. So I'm just going to give them to you. So if you were wondering in your lab, where does this period formula come from? This lab is hitting too early. I have no illumination for you at this stage either. Okay? I'm just going to give you the formulas. We'll try to get some intuition as to why they seem sort of correct, but they're just kind of intuition. There are going to be parts of the equation that we cannot justify at all. So that's what we're going to do with these two systems. So before I do anything, before I even start these systems oscillating, I have not yet talked about a spring at all. So we need to do a little bit of a background on how a spring works. You may remember in this lab that you first had to measure the properties of the spring before you can start to oscillate it. So let's talk about that. How do springs work? So this is a spring intro. So I'm going to have a flat horizontal surface, frictionless. I'm going to put a mass onto it. And of course, the reason why I want to have it be a horizontal frictionless surface is that basically then the object experiences no net force from its environment, except I'm going to put in a spring. So the only thing that happens to this mass will be due to the fact that I attach a spring to it. Now, a spring has an equilibrium length. So this may be where the end of the spring is to be in equilibrium, and if so, that's its happy place. So the spring exerts no force at all. Every spring has an equilibrium length, a happy place, and the spring only starts to exert a force if you take it away from there. So for instance, if you stretch the spring, let's pull the mass over here, you've stretched the spring like this, then you will get a force. And the spring force will be back towards equilibrium. It's saying, hey, I like that happy place. Why are you taking me away from it? I want to go back to it. Likewise, if you compress the spring, I know this is getting a little messy, also the spring wants to push back there. So that is the essence of a spring, is that it has a certain place where it likes to be, and it complains and wants to go back there if you take it away. So the spring force, it is 0 if at equilibrium. It's towards equilibrium otherwise. This kind of force gets a characteristic name. It's called a restoring force. Right? That's what the word restore means. It means it wants to get back to some kind of thing, right? So this force always pushes towards a common place. Now notice that makes it a relatively complicated force profile because it can point right or left depending on which way, which side of the happy place you're on, right? So right away, the force is not going to be constant. At the very least, it will switch direction, right? If you shoot through the equilibrium, then the force will switch direction completely from one direction to the other. Now, if that wasn't complicated enough, it turns out that the amount of force on both sides is not a constant. So not only is the force always towards equilibrium, but the further you take the spring from its happy place, the more it complains. So it turns out that you can measure how much the spring is displaced from its equilibrium, and the larger that is, the more the force will be to try to get it back there. In fact, there's the spring force law, which is also called Hooke's law, says that the spring force is directly proportional to that displacement. Which is to say, if you take it twice as far from its happy place, the spring will complain twice as much, right? Twice the displacement from equilibrium, twice the force. And To complete the equation, we put in a variable k. And the k is what's meant to describe the fact that obviously not every spring is exactly identical. Okay, so k is called the spring constant. It's the stiffness of your spring. I put it in quotes because stiffness has a technical definition that's slightly different, but for our purposes this is going to be more than fine. That accounts for the fact that the spring, some springs are more loose, as you may know, and some springs are more stiff. Basically, if k is larger, then the spring is stiffer. So, let's talk about this equation. First of all, if you solve for the units of the spring constant, what's units of force? Newtons. And then what do we have to do to get the spring constant? Divide by meters. So the units of spring constant are newtons per meter. For example, if you have a, let's call it spring number 1, you rummage around in your box and you get a spring. Let's say that your spring has a spring constant of 5 newtons per meter. That is a property of the spring. What it tells you is that this spring will exert 5 newtons of force for every meter that you take it away from its happy place. Take it away from equilibrium. So for instance, if your displacement was 1 meter, then putting it into the formula, your spring constant is 5 newtons per meter multiplied by 1 meter. The force will be 5 newtons, right? So k times delta x gives you the force. Now if you take this spring and you displace it not 1 but 2 meters from equilibrium, well the spring still exerts 5 newtons per meter. That's a property of the spring. That's a stiffness. That is a property of the spring that doesn't change unless you break the spring, I guess. But now that you're stretching it 2 meters, how much force will it exert? 10, right? The meters cancel, you get 10 newtons. So there's no one answer for how much force a spring exerts. The force is not constant. The force will grow as you take the spring further away from equilibrium. But what is constant about the spring is k, it's spring constant, it's stiffness. That doesn't change. Okay? So for instance, if you had a second spring, spring number 2 might have a spring constant of 10 newtons per meter. This spring is stiffer. It'll exert 10 newtons of force for every meter that you stretch or compress it. So now, if you take that spring and you displace it by 1 meter, how much force is that going to exert? 10 newtons, right? So that spring exerts 10 newtons of force when you stretch it for only 1 meter, whereas over here, this spring, we had to stretch it to 2 meters before it exerts that much force, right? So it's because this spring is stiffer. It has 10 newtons per meter of spring constant instead of just 5. So k is a property of the spring. That doesn't change. It's a property that goes with the spring, but the amount of force is not the same. Okay? Are there any questions on that? Yeah.
So if your equilibrium is that point and you're pushing it this way, would your delta x be negative?
Right. So we are going to take our springs to be symmetric for both stretching and compression, right? So it doesn't matter if you stretch it 1 meter or if you compress it 1 meter, the force is going to be the same. This equation I intended to just be a all magnitudes. So this is like size of, and k is always positive. It amount. You can, if you want to, combine both of these concepts into a single formula. So we haven't usually made the habit of doing that, but I will show you in this case. Normally when we talk about a force, let's say the force of gravity, we talk about the size and direction separately, right? So we say, here's how big it is. The force of gravity is mg, right? G isn't negative, so that's just an amount, right? Or if we want to use the universal law, we say this is the amount, right? And then we separately say that the direction is attractive, right? And attractive we can turn it into some kind of mathematical language, right? If we decide that downward is negative, then we might call it negative, right? So for the spring force, I'm going to suggest that we split it up into two pieces, one of which just gives us the amount. And for that, we're just going to use everything positive. We're not going to worry about direction, right? And then the direction is, of course, towards equilibrium. Now, it is possible to bundle up both of these into a single statement because the law is simple enough, and that statement looks like this. So here, we put in the vectors, right? So here, we could, for instance, say if the displacement is positive, right? If we take the spring and we call this the positive axis, right? If we take this to the positive, well, this should be negative, right? And for that reason, you're going to need an extra minus sign here to make it work out. Basically, this minus sign is what makes sure that the force is towards equilibrium. It's the mathematical encoding of this idea, right? Likewise, if you compress the spring, right, you make the displacement this way, and that's negative, then the spring force has to be the opposite way, right? So that's going to be positive. That extra minus sign here makes sure that that's the case. It's basically that minus sign makes sure that the displacement is countered by the force not liking it, wanting to pull it back. You'll often see Hooke's law, the spring force law, stated like this, but I do want to point out that there is no reason to have to use that form. You just work with sizes over here and worry about encoding the direction separately, just like we did in any other force. Does that make sense? And so this is called Hooke's law. This is what back in the day passed, like if I gave you a spring and a half an hour, you could figure out Hooke's law, and yet this guy has his name on it forever, okay? That's what, this is when science, there wasn't a whole lot figured out. You spent the afternoon in the lab and get your name on something forever, okay? It's not that easy anymore. Basically, his discovery was the force on a spring is directly proportional to the displacement, okay? So that's our background in the spring, and we're ready to go now. Let's talk about how a spring works when you're oscillating something. So let's go to the mass limit spring oscillation. So let me sketch this. So here's going to be my equilibrium. And I'm going to draw my mass over here. Let me draw mass over here, then here, then here. I guess I'll draw it going through the equilibrium. And let me not draw the spring, because obviously if I try to draw the spring attached to all these, it's going to be a whole mess, right? But you can imagine there's a wall over here, and the spring connects the wall to each of these masses, right? Or these aren't different masses, it's the same mass that's oscillating, right? So let's talk about the properties of this oscillation. First of all, displacement. So the displacement from equilibrium is 0 here. And then, of course, the displacement is maximum over here. Maximum size. Actually, let me make this even maybe a little more cleaner. So I'll put the displacement from equilibrium. It's max here, 0, and max here. Okay? So it's 0 when you're at equilibrium. It's maximum when you're furthest from equilibrium. Let's write down the acceleration. That's probably the next easiest one. The acceleration, well, of course, that comes from the spring force, right? The spring force is the net force, right? I don't have any others. So as goes the spring force, so goes the acceleration. That's the essence of Newton's second law, right? That whatever's the direction of the force, that's the direction of the acceleration. So let me draw the acceleration. The force is 0 here, so the acceleration is 0. The force always points towards equilibrium, so the acceleration is going to be like this. And what happens to the size of the force as you get further from equilibrium? Bigger. So what happens to the acceleration? Bigger. In fact, the acceleration is maximum out here too. So, just like we have a restoring force, which always points toward the middle, we always have that the acceleration is toward the middle. So, with that in mind, let's write down the velocity. Now let's suppose that we release it from rest somewhere out here. Why wouldn't we want to release it from rest at the middle? It wouldn't do anything, just stay there, right? It has no acceleration to do something else. So let's release it from rest over here. Now it's not going to stay at rest because it's going to have an acceleration applied. So the velocity is going to pick up like this. And of course, since the velocity and acceleration are pointed the same way, what does that mean happens?
Speeds up.
Speeds up. So you're going to speed up going towards the equilibrium. Now, when you get to the equilibrium, the acceleration is 0. Does that mean you stop dead? No. You built up all this velocity getting there, and now you have it. In fact, your velocity here is going to be maximum. You've spent your entire journey to this point gaining velocity, right? The acceleration was with you the whole time. Now, why do I say it's the maximum? Well, what's going to happen when you overshoot the equilibrium and keep going to the left? Well, the acceleration is going to start working against you now, right? So the fastest you can ever go is when you go through equilibrium, because when you get to there and you overshoot, now the force and acceleration are going to start acting against you again. So you're going to start slowing down, because now the velocity and acceleration are opposite. So you're going to slow down. And how fast are you going to be going at the other extreme? Stop. So your velocity is 0 again out here. I didn't draw a circle 0 with a slash through it on the other side, so let's try to be consistent, right? So you stop there for at least a moment, but do you stop there permanently? Well, no, because of course we know if you apply an acceleration opposite your velocity long enough, you'll stop, turn around, and speed up the other way. And what are you going to do then? You're going to speed up as you go towards equilibrium, overshoot it, and then bounce and bounce and bounce and bounce. And if there's no friction or anything to take energy out of this system, it's just going to do it forever. So that's where the oscillation comes from. Okay? The oscillation comes from the fact that you release it somewhere besides the equilibrium. The spring always pulls you toward there, but by the time you get there, you've built up velocity to overshoot it. Right? That is where oscillation arises. Does that make sense? So the common theme here is that you speed up going towards equilibrium, and you slow down going away from it. So that's kind of a theme for how the velocity evolves. It means you have V max at the equilibrium because you finished speeding up and you haven't yet started slowing down. And it, of course, also means you have zero, you're going zero speed at the extremes. So that's where your oscillation comes from. This kind of restoring force can lead to oscillation. The force always pulls you toward the equilibrium. You always overshoot it when you actually get there. So you can see, of course, the acceleration profile is very, very complicated, right? The acceleration not only diminishes in amount, but it turns to zero completely and then switches to the other direction and grows, right? So the constant acceleration equations are out the window here. We can talk concepts, but we don't have any equations to hang our hat on, right? Remarkably, we can still even say what happens even with the acceleration being so all over the place. This is where we really have to remember that even though the acceleration is changing its amount, going from here to here, even if it's changing its amount, the velocity is the same way, so you're still going to speed up, right? The velocity and acceleration being the same direction means you're going to speed up even if the acceleration is varying its size, right? And the velocity and acceleration being opposite, you're going to slow down. So even if the acceleration is changing its size. It's just like you're driving around with your friend who seems to have a terrible brake foot, right? Everything stopping with them, it's always herky-jerky, right? Because they can't seem to apply a constant acceleration with their brake foot. You still slow down though, right? It's just in a more herky-jerky manner. And this is too. You're going to experience your biggest velocity changes out in the extremes because the acceleration is very large. By the time you approach the middle and the acceleration is turning to zero, the best characterization for how you pass the middle is your quote-unquote coasting, right? So your velocity doesn't change very much toward the middle. It's mostly changing on the extremes. Maybe you notice that when you're watching your thing bounce around. It almost looks like it's constant speed and then it suddenly jerks and reverses, right? It's because if I were to try to kind of generalize, here you're kind of coasting-ish, right? And then here you have your big changes on the extremes. Big changes to the velocity. Now obviously, there's no magic cutoff. It's more that the more you're closer to the middle, the more you're coasting, right? The more you're approaching zero acceleration, so the more you're approaching just keeping the velocity you have. I like to describe it as you're coasting toward the middle and you have big changes in the wings, okay, in the outskirts, right? That's where the force and acceleration from the spring are strongest, most strongly opinionated, right? So, this is an important profile because every system that oscillates has a profile like this. That's what makes it oscillate, okay? And we're in the pendulum system, same deal, okay? So in the pendulum system, guess I'll just mention it briefly. The pendulum system, this is your equilibrium. A pendulum, if you just hang it like that, it just stays in place, right? What is it that gives the restoring force in this system? Well, the thing that drives the pendulum is obviously not a spring, it's gravity. Now gravity, at this stage, is pulling straight down, which, by the way, is straight out of the hinge. So what happens if you, like, say, try to open a door by pulling outward on the hinge? Nothing. So the problem here is there's no torque. Instead of there being no spring force, at equilibrium there's no gravitational torque. If you take it somewhere over here, well, of course, gravity is not going to change. It always pulls downward. And now downward is not out from the hinge anymore, right? If we were to sketch this circular path, well, of course, there is a component of force which is tangential now, right? We're going to get some torque. And the torque, not surprisingly, is back that way. And as goes the torque, so goes the angular acceleration. Likewise, if you take the pendulum over here, the torque and angular acceleration are toward the middle again. So notice there's a common theme of oscillating systems. They oscillate around some equilibrium where there's no force or no torque. But if you take something away from there, it wants to go back there, right? So all you really have to do to understand the profile of a pendulum is switch your force and displacement from equilibrium, which always, let me do the force and acceleration, have to switch that to gravitational torque and angular acceleration. Instead of displacement from equilibrium, angular displacement from equilibrium. And instead of v, omega. So we now have, as I listed at the beginning of class, we said we were looking at three aspects of these systems: the kinematics, energy, and period. We've just finished the kinematics for both systems. Okay? So if you can't see that they're exactly the same idea, maybe take some time to build this kind of play-by-play for the pendulum system at home. Okay? And if you have any questions, let me know. So let's move on. Are there any questions on that before I move on? Okay, so hopefully these are some concepts. These are the kind of good things that are good for multiple choice questions, but I can't ask you to calculate anything. I've hopefully convinced you the acceleration is nowhere near constant, so we need to move to energy. So let's move to energy. In the spring system, the kinds of energy that are being traded are translational kinetic energy and spring potential energy. This is the mass on a spring system. For the pendulum system, what's being traded is rotational kinetic energy and gravitational potential energy. So remember, energy is just another picture, right? It's a complementary way of looking at things. Instead of saying that something speeds up and slows down during the oscillation, we say that it gains or loses kinetic energy, right? So, out of these four forms of energy, we know three of them already. In fact, this might be a good time to take an energy survey. We talked about this idea of mechanical energy. Mechanical energy comes in two forms: the type that you can see and the type that's stored and you can't see it. type that you can see, energy of motion, is called kinetic energy. And then the type that you can't see, it's in storage, we call potential energy. At this point in the course, we saw that energy of motion, well, you can have energy of motion in two different motions, translational and rotational. In fact, that was the big topic of last lecture, right? The disk in the ring racing down the incline. They have both kinds of those kinetic energies. And we are now introducing a second form of place you can store energy. We said gravity can store it, but of course, now we're going to say that a spring can store it. Which hopefully does not come as a surprise. If someone hands you a spring that's compressed, you know what's going to happen, right? It might fly out, right? That energy that's stored in the spring might fly out in your face, right? There's those jack-in-the-box things where the spring comes popping out. It's like old-timey prank, right? So this right here is a kind of a master survey. There's at least going to be one problem on your homework 10 which includes all four of these. Okay? These two, of course, are the only two forms that are eligible for your upcoming exam, and you should know those cold. But last lecture we introduced rotational kinetic energy, and now this lecture I'm introducing spring potential energy. And let me also remind you that even mechanical energy, with all these different forms, there are still other forms which we take care of with this kind of in and out valve, right? So this is where heat can leave, and chemical energy can come in, all these different things we've looked at on your homework number 8, I think. Or 7, I can't remember which one's your big energy homework. 7? I think it's 7. All right, so let me tell you what the formula is. I don't want to derive it because I don't think it's worth our time. The formula for spring potential energy is 1/2 k delta x from equilibrium squared. I guess I can briefly sketch out how I did that. Well, we have our good old work formula. And we said that work changes kinetic energy, and if it's a conservative force, we can say that the energy is fully exchangeable, fully refundable, and so we can say that there's a potential energy. So, what do we have? Delta x. The force itself is k delta x. So, k delta x times delta x, that's k delta x squared, right? And if you're wondering where the half comes from, the half comes from the fact that if you have some kind of motion, you have to use the average force over that motion. So if the force grows from 0 to k delta x at the end, then the average force is going to be half of that. So that's where the half comes from. Okay? Because we have never really looked at a case before where the force is changing out from underneath you throughout the motion, right? We only usually work with constant forces, right, for doing work. But if you have an object that's moving against the spring, it's displacing against the spring, the force is different at the beginning and at the end. So you have to take the average. And it turns out in this case, the average between 0 and final is just halfway. So that's where the 1/2 comes from. Again, hand wavy, I know. I just want to move forward. If you're wondering, that's sort of an answer. If you're not wondering, you can just move forward. Okay? So notice that this equation says that the displacement from equilibrium is 0, the spring stores no energy. Which hopefully makes intuitive sense, because if you release the spring there, nothing will happen. There's no energy that is stored that you could have come out, right? The spring doesn't store any energy when it's at its happy place. But the further you take it from its happy place, the more energy it'll store. And if you're not careful, that potential energy may get converted into kinetic energy when you release it. So you better be aware, not have your face in front of that spring. Okay? So let's set up a typical energy conservation problem that would work here. Let's say, for instance, I release an object from rest over here. I'm going to say that the distance from equilibrium that I release it from rest is called A. Why am I not calling it displacement? Well, displacement is a generic term for how far you are away from the equilibrium at any given moment. But the maximum value, we often call A. A stands for amplitude. You may already be aware that that's a common English word that is used when you talk about something that's oscillating. Amplitude indicates how extreme is the oscillation, right? So amplitude is a word for how extreme it is. How do I know it's going to be the extreme? Well, I'm releasing it from rest, right? So it can never get any further than that. I'm going to ask, how fast is it going through equilibrium? And we already established that that is Vmax, right? The maximum speed you can have. That's what you're going to spend all your time speeding up, going towards equilibrium, and you haven't yet started slowing down after you've overshot it. So let's go ahead and do it. This is my initial, this is my final. My given variables are going to be A, and also I'm going to give you the spring constant. I need to know about the stiffness of the spring. As you can imagine, a stiff spring is going to get this going a lot faster, right? And let me also give you the mass that it's pulling on. So I go ahead and I set it up. It's always good to start from the top master energy equation, except for this case, of course, I'm going to have it be frictionless, so I don't have to worry about that. I'm not going to have any rotational kinetic energy, and I'm also not going to have any gravitational potential energy. It's all happening on a level surface. So I only really have two forms of energy I need to worry about: KE translational and spring potential. Final. So let's let the simplification begin. How much kinetic energy do I have at the initial point? Zero. I'm stopped. You only have kinetic energy when you're moving. You don't have any. How much potential energy do I have at the end? Zero, because I'm at the spring equilibrium. So the spring doesn't store any energy there. So this is just a case of all the energy that was initially stored in the spring is going to be available to us as kinetic energy. Now, the acceleration was certainly not constant between these 2 points, but the beauty of energy method doesn't care, right? So let's go ahead and just plug and chug. This is going to be 1/2 k a squared. A is the initial displacement. And the final kinetic energy, 1/2 m Vmax squared. Speed at the final point is Vmax. So we go ahead, cancel the halves, solve for Vmax. That's going to be square root of k over m times a. That is the solution to this problem. This is an example problem. This is not meant to be a derivation. You should not be applying this willy-nilly to other problems. If you do, you're missing the point of physics generally. You want to start from physics first principles and work through. Okay? Physics is not about plugging and chugging. So this is the symbolic solution to this example. And you should be able to follow the steps like I follow the steps and be able to account for other cases. For instance, maybe I started it with an initial push, right? Then I would not set the initial to 0, things like that. Let's take a look at the answer and see if it makes sense. So proportionalities are always worth checking. According to this equation, if my A is larger, what should happen to V max? Larger. They're directly proportional. If I double the amplitude, I'm going to double V max. Does that make sense to you intuitively? If I pull this back further, it'll go faster through the middle? Yeah, right? I pull it back more, I'm going to store more energy. Well, remember that the energy stored depends on how much I pull it. So if I store more energy, that more energy stored can come out as more kinetic energy, right? That's also true if I increase the spring constant. If I have a stiffer spring, it can get me going faster in the same distance, right? Those are not, by the way, directly proportional, right? So if you multiply the spring constant by 4, how much would the maximum speed be different? V max is proportional to the square root of k. So if k is 4 times its previous amount, what will that do to V max?
2.
2, exactly. And then finally, the mass, right? If I increase the mass, what does that do to V max?
Smaller.
Smaller. More mass, more inertia. More inertia, more stubborn. It changes. It's not going to get going as fast. You can't, a bigger mass pulled by the same spring is not going to react as strongly, right? That's an inverse square root proportion, right? That would be another fun one, right? If you quadruple the mass, the V max will be half, right? Things like that. Okay, so that'll be a good breaking point for today. I'll do the energy exchange in the pendulum next time, and then move on to the period formulas.